Okay, Chapter 6, Section 6.1 on equilibrium and 6.2 on dynamics. Equilibrium. An object on which the net force is zero is in equilibrium. There's two kinds of equilibrium. If it's at rest, it's in static equilibrium, and if it's moving along a straight line with constant velocity, this is dynamic equilibrium. So a bridge would be something that's in static equilibrium. In either case, the requirement is that the net force in the x direction and the net force in the y direction is equal to zero. And in both cases, the net force component is the sum of the components of all the individual forces acting on the object. So your strategy here, you model the problem, perhaps represent the object as a particle. You draw a diagram, define your symbols, identify all the forces acting on the object and show them on a free body diagram, and then use F net equals 0 to solve your forces. At the end, check your result has correct units, is reasonable, and answers the question. Section 6.2 is on using Newton's second law. So all of Newtonian mechanics, or the basics of it, can be expressed by two steps. First, you determine the acceleration based on acceleration as the net force divided by m. And the second step is once you know the acceleration, you can find the object's trajectory. So to solve a dynamics problem, you model the problem, you draw a diagram, establish a coordinate system, define symbols, use a motion diagram to determine anything you might know about the object's acceleration, and identify all the forces on a free body diagram that are happening at a particular instant. And it's okay to go back and forth between these steps as you're visualizing the situation. To solve it now, you use that the net force is equal to m times the acceleration. Okay, and the vector sum is found by looking at the free body diagram. You can solve for the acceleration and then use kinematics to find velocities and positions, or you can use kinematics to determine the acceleration and solve for the unknown forces depending on what you're trying to find. And at the end, of course, check that your result has correct units, is reasonable, and answers the question. Okay, section 6.3 on mass, gravity, and weight. Mass is an intrinsic property. Here is a simplified view of the essential properties of a pan balance. The way it works is you have known masses on one pan, which is connected by a pivot to some unknown mass sitting on another pan. And if the unknown mass differs from the known mass, the beam will rotate about the pivot. The pans balance when the masses are equal, and both pans are pulled down by the force of gravity. So this measurement of the unknown mass does not depend on what the strength of gravity is. It's a comparison between these two masses. Mass is a scalar quantity that describes an object's inertia. Mass describes the amount of matter in an object. Okay? It's an intrinsic property of the object. It doesn't change depending on where the object is. Gravity is a force. It turns out that gravity is an attractive long-range force between any two objects. Here we have a figure showing a mass m1 and a mass m2 whose centers are separated by a distance r. Each object pulls on the other with a force which is equal to capital G times m1 times m2 divided by r squared, where G is this universal constant 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. The gravity force between any two objects is negligibly small. We can almost never measure it, okay? Unless one of the objects is a planet. So here on Earth, if you have a mass near the Earth, near the surface of the Earth, then there will be a force of the planet Earth on the little mass m. and it will be equal to g times the mass of the Earth times the mass of the object divided by r squared, where r, capital R, is the radius of the Earth, which is approximately the distance between the center of the little mass, and lowercase m, and the center of the Earth. So here it's just gmm over r squared, where m and r are the mass and radius of the Earth. And you can also express this equation as lowercase m times lowercase g, where g is 9.8 meters per second squared. So here we have lowercase g defined in terms of uppercase G times the mass of the Earth divided by the radius of the Earth squared. So if we set up a coordinate system where y is up, x is to the left, then the force of gravity is in the negative y direction. So here's a free body diagram of an object that's in free fall. So the only force acting on it is the force of gravity. So the acceleration due to free fall is the net force divided by the mass, which is mg over m, which just turns out to be g, straight down. All objects on the same planet, regardless of their mass, have the same free fall acceleration. Thirdly, weight is a measurement. If you go to a grocery store, you might see a hanging spring scale, which contains a spring which is attached to a little dial, and when you put a mass underneath it, it stretches the spring a certain amount and the dial reads off the force. Okay. We define the weight of an object as the force reading of a calibrated spring scale on which the object is stationary. Okay. At F sub SP, the spring scale is a force, so weight is measured in newtons, in the SI units. A bathroom scale is similar, except it's pushing. It's got springs that push up, and the amount that these springs are compressed is read off on a dial that you look at. Okay. So if you have an object here and it's not moving, the net force on it is 0. So that means that the spring force exactly cancels the force of gravity. Force of spring equals force of gravity equals mg. So the weight of an object that's sitting on a stationary scale is equal to m times g. But what if the scale is accelerating? Here's an elevator that is accelerating upwards. Okay. If you look at the free body diagram down here, there's a net upward force which is causing the man to accelerate upwards, so the spring force upwards must be greater than the gravity force downwards. So F spring minus mg equals m times a sub y. So as this man accelerates vertically, the reading on the spring scale, W, okay, which is the same as F sub SP, is equal to mg times 1 plus a sub y over g. So you actually weigh a little more as you accelerate upwards in an elevator. So here's that same equation again, mg times 1 plus a sub y over g. If you're accelerating down, then you will weigh less than mg. And in fact, if your acceleration is negative g, then this will be 1 minus 1, and your weight will be 0. An object in free fall has no weight. Okay. Astronauts orbiting the Earth are also weightless. Does this mean that they are in free fall? Yes. As you orbit the Earth, your acceleration is towards the center of the Earth, and it's equal to g. And so that's why your weight is 0 in space.